Welcome back to Mechanical Engineering Made Simple. Ever wondered why a paperclip just bends when you fiddle with it, but a glass window shatters into a million pieces? Or how a steel cable can hold up an entire bridge, but if you bend that same cable back and forth, it just snaps? Well, the answer is hidden deep inside the material itself, in this invisible world of pushing and pulling forces. Today, we're digging into the science of material strength. We're going to find out why things bend, why they stretch, and, most satisfyingly, why they snap.
So let's get right to it. What actually makes something strong? It sounds like such a simple question, but the answer is way more interesting than you'd think. See, it's not just about how much force something can take. It's all about how a material behaves on the inside when that force is applied. And to really get it, we need to look inside the material itself.
Okay, to get our heads around this, we're going to start with the absolute simplest thing you can do to an object. Just pull on it. This is called tension, and it's the perfect way to introduce the two most important concepts in all of material science: stress and strain. Picture this. We've got a simple steel wire, just hanging from the ceiling. Now, we start adding weights to the bottom, one by one. As we add more weight, which is just another word for force, the wire starts to stretch. It gets longer. Now, that seems totally obvious, right? But what's really happening inside that wire is a constant, invisible battle.
So, the first big idea we need to tackle is stress. You'll see it written as the Greek letter sigma. Now, here's the key thing. Stress isn't the weight we're hanging on the wire. Stress is the internal force the wire itself creates to fight back. It's the material basically screaming, hey, you are not pulling me apart that easily. It's that internal resistance spread out over the area of the wire.
And what happens when the material is under all that stress? Well, you get strain, represented by the Greek letter epsilon. Strain is the thing we can actually see and measure. It's simply how much the wire has stretched compared to how long it was to begin with. It's just a ratio, so it doesn't have any units, which is kind of neat. It's just a pure number that tells us how much it has deformed.
So here's the bottom line. The one thing you absolutely have to remember. Stress is the cause, strain is the effect. Stress is the invisible fight going on inside the material. Strain is the visible result of that fight. You get this relationship, and you've unlocked the secret to pretty much everything else in material science.
Now here's where it gets really cool. If we plot that relationship, if we track how much internal stress is building up for every tiny bit of strain, we get something called the stress-strain curve. And honestly, you should think of this curve as a material's biography, or maybe its personality profile. It tells you the entire story of how that material is going to act under pressure, from the first gentle pull all the way to its catastrophic end.
Let's check out the personality of a real workhorse material, mild steel. As we start pulling on it, the stress and strain go up together in a nice straight line. That's the elastic region. If we let go anywhere in this zone, it snaps right back to its original shape, no harm done. But then we hit the yield point, and that's the point of no return. The material has started to permanently deform. It gives up trying to go back. As we keep pulling, it actually gets a bit stronger for a while. That's called strain hardening before it reaches its absolute maximum strength, the ultimate stress.
This whole behavior makes mild steel what we call a ductile material. Ductile materials are, well, they're the forgiving ones. They bend, they stretch, they give you a ton of warning before they finally fail. You see that thinning area that happens right before it breaks? We call that necking. And it's a huge visual clue that things are about to go very, very wrong. It's exactly what happens when you bend a paperclip back and forth.
Okay, now check out the contrast on this slide, because this is fascinating. On the left, there's our ductile steel with its long, drawn-out failure story. But on the right, we've got a high-strength steel, which is a brittle material. And just look at that curve. It's a straight shot up, up, and then it just stops. There's no warning, no yielding, no necking. It just snaps.
And that's the whole deal with brittle materials. They are incredibly strong right up until the moment they're not. They give you almost no warning, no plastic deformation before they just fracture completely. Think about a pane of glass or a ceramic coffee mug. They don't bend, they just break. This is also why concrete is so weak if you try to pull on it. It's a brittle material and just can't handle stretching.
All right, so we've covered pulling things apart and squishing things together, but forces don't always act head-on. What about forces that try to slice through a material or make one layer slide past another? For that, we need to talk about a whole different kind of stress, shear.
This is shear stress. And we use the Greek letter tau for it. The best way to picture it is to think about a deck of playing cards. If you push on the top of the deck, the cards all slide past each other. That sliding force between each card is a perfect analogy for shear stress. It acts parallel to the surface, not straight into it like tension or compression.
And once you know what to look for, you see shear everywhere. The rivets holding the plates of a bridge together, they're under intense shear, fighting to keep those plates from sliding apart. The same goes for the bolts in your car's engine. Heck, even using a hole punch is a classic example of causing shear failure. You are literally shearing a little circle of paper out of the main sheet.
And here's a little mind bender for you. Even when you're just pulling on a bar in simple tension, you are creating shear stress deep inside it. But the wild part is, the maximum shear stress isn't straight across the bar. It's actually acting on planes that are at a 45-degree angle to the direction you're pulling. These forces are always connected in surprising ways.
So, in the real world, these forces hardly ever show up to the party alone. They're all mixed together. A simple beam holding up a load is the perfect place to see this complex dance between tension, compression, and shear, all happening at the same time.
Let's take a look at this cantilever beam. It's just a beam that's fixed at one end, with a force pushing down on the other. It looks about as simple as it gets, right? But believe me, inside that beam, there is a total war zone of competing forces raging at every single point along its length.
So as the beam bends down, it's pretty intuitive that the top fibers are getting squished together, that's compression, and the bottom fibers are getting stretched apart, that's tension. Simple enough, but what's stopping the top half and the bottom half from just sliding past each other? What's holding it all together? And this is where shear comes back in as the unsung hero of the story. The shear stress isn't the same everywhere in the beam. In fact, it's zero at the very top and very bottom, right where the tension and compression are the strongest. The shear stress is at its absolute maximum right along the neutral axis, dead center in the middle of the beam. That's where it's working the hardest to keep the beam from tearing itself apart.
So why do we care about all these invisible forces? I mean, why go through all this trouble? Well, because understanding them is literally the only reason our buildings are still standing, our planes stay in the air, and our bridges don't just collapse into the river. It's the absolute bedrock of safe engineering.
At the end of the day, every single structure you rely on is the result of a very careful set of calculations. Engineers have to understand exactly how stress, strain, and shear are going to affect every single part, just to make sure those internal forces never, ever exceed what the material can handle.
The whole process really boils down to this three-step dance. First, you analyze all the forces that are going to act on the part. Second, you pick a material that has the right personality. Do you need something ductile that will bend and give a warning, or something brittle and rigid? And finally, you design the exact size and shape to guarantee that the internal stresses always stay in the safe zone, far, far away from that material's breaking point.
So the next time you walk across a bridge, or fly in a plane, or even just put a heavy book on a shelf, take a second to think about that silent, constant battle happening deep inside the material. That invisible war between stress, strain, and shear that quite literally holds our entire world together.